Practice exam, Unit 3. So I had 4 nomenclature problems. All of these were to take a name, or 3 take a name, and then 1 take a structure and turn it into a name. So find the parent name, cyclopentene, so 5-membered ring. 1 is for the alkene, and then 4 bromo. 1, 2, 3, 4. There's your bromo. Parent name here, butene, 2-ene. So draw 1, 2, 3, 4. 1, 2, 3, 4. 2, 3 dimethyl. 2, 3 dimethyl. So 2 methyls, carbon 2 and carbon 3 are where they're located, and then 1 chloro on carbon 1. Moving down, pentyne. 1, 2, 3, 4, 5. So I just had no 5 carbon chain, pent, ine for alkyne, and say 1, because it's on carbon 1. 2 methyl hept 3-ine. Again, find the parent name, hept 7. I would draw the alkyne first because bond angles matter. So draw the alkyne first and then move off of that. 1, 2, 3, 4, 5, 6, 7, and then 2 methyl. So draw the alkyne first. There you are. One of the ones you've seen before, right? One of the ways you do these carbocation rearrangements. If you saw this, draw the mechanism. You probably noticed went from a 4-membered ring to a 5-membered ring. That should set alarm bells off, telling you that there's going to be some sort of rearrangement. Pi bond reacts. Pi bond's nucleophile. Makes a secondary carbocation. Sigma bonds 2 bonds away can open the ring up and expand it. Kind of drawn not so pretty here, but there's the carbon that lost a bond. Tertiary carbocation, you can't make it any more stable. There's no pi bonds or lone pairs for resonance. Solvent reacts, protic solvent, also something to look for. Solvent reacts, deprotonate. Don't forget to balance your charges. H falls off to remake H plus in the last step. Number all the carbons, 4 points, and add lone pairs. And then add in mechanism arrows. Right, pi bond reacts, this is an alkyne. Excess HCl, carbocation and the more substituted carbon. No rearrangements with alkynes. Nucleophile reacts, chlorine adds in. Now we have an alkene. Alkene reacts with HCl, makes a carbocation. Why does it make it on that side? Well, I told you where it goes, but 3 also could be stabilized by resonance, which we'll see in a second. Chlorine adds there. Adding the lone pairs, plus 1 for each arrow. So just following along, bonds broken, bonds formed. So kind of taking this, so draw a resonance structure of the molecule below. So this is one of those intermediates from above. It has the chlorine, and then the carbocation is 1 bond away. So you can do resonance, right? Even though the chlorine has a positive charge, everybody has a full octet in this molecule. So that's more important, right? The octet rule is the most important thing. So the more stable one is the one that has a full octet. Oh, right. So number 5 here is a challenging one. So I fill in the box here, but what I needed people to recognize, I was looking for people to recognize. So here's an alkyne, and it has 1, 2, 3, 4, 5, 6 carbons, and all of a sudden it has 2 pi as an alkyne. And I had Na, NH2. So this is really Na, right? And I wanted you to recognize that as a strong base and think E2. Right? We've used this strong base to do E2 reactions, which I'm looking for here, or to deprotonate terminal alkynes. So in this case, you need 2 leaving groups because, right, I'm forming 2 pi bonds. So that's a double E2. And the 2 leaving groups could be on the same carbon or they could be on 2 opposite carbons. Either way is fine. But the key is recognizing, how do I make an alkyne? How do I make an alkyne? This reagent tells you, oh, that's one of the ways to make alkynes from a double E2. Then in the second step, these 2 things are blank, but I want you to look over here. So if you were looking over here, you might have recognized all of a sudden there's an extra carbon, right? Here we had 1, 2, 3, 1, 2, 3, and obviously we have these 3 carbons down here, but an extra carbon showed up. You really only know one way to add an extra carbon. And that's by deprotonating a terminal alkyne, right? Because there is an H here, we just don't draw it in, right? Again, Na plus NH2 minus here can deprotonate And then this can do an SN2 to add that extra carbon to the end of a terminal alkyne. All right, so that's one of the ways you know how to add carbons. That's really the only way you know how to add carbons, is that. And then once we have an alkyne, to reduce it all the way, H2 palladium on carbon, you assume H2 is always in excess. So you keep adding hydrogen until there's no pi bonds left and you get this product. Yeah, good question came up. How did I decide on Br? I could have just said leaving group. It doesn't matter. Bromine, whatever's a good leaving group for an E2 reaction. So honestly, I don't care if you wanted to write just Lg for leaving group, that'd be okay too. So yeah, bromine I just picked. You could have picked chlorine. You could have picked iodine. You could have picked any other leaving group you want. But you need to have a leaving group. So this problem is challenging. Write down what you know. You could easily recognize a carbon was added. You could write, I need to add a carbon, right? You could say, I know one way to add carbons, right? I need to make pi bonds, right? Write down what you know to earn points, right? It's worth 6 points, right? These are really challenging problems, but write down what you know and do your best. Don't let a hard problem affect all the other problems that you do know, right? Next one, pi bonds nucleophile. Pi bond reacts HCl, carbocation here. I know it's there because that's where the product ends up. Pi bonds nucleophile. I put the carbocation here because that's where the chlorine ends up here. Pretty standard stuff. The next question, though, which is more likely? So the one that's actually more likely is very similar to the question before this, a couple back. This product A is more likely because this carbocation can be stabilized by this oxygen having lone pairs, right? Resonance stabilized. And take a look at that, right? You can see it. I just drew it in here. There's lone pairs here, and you can draw a resonance structure with full octets. So product A is more likely to happen. Nice. Give the mechanisms and products for the tautomerization reactions below. So if you see tautomerization, you should immediately recognize that these enols are going to be turned into ketones, right? Or carbonyls. So one of the things you could have done right away before you even draw the arrows was just to draw this. That if you see this, you recognize, oh, there's going to be a pi bond here and this H is going there. Pi bond here, right? Just to recognize those things, that'd be a good thing to do right away. Either case, in all these tautomerizations, pi bond's still the nucleophile. Have your arrow start the pi bond for the H. This OH bond breaks. That forms the new pi bond there. H plus is this H plus, which fell off. This is acidic conditions. In neutral conditions, it's all in one molecule. Pi bond grabs the H. The electrons in this OH bond go here to form that pi bond there. All in one step, 2 arrows. A couple multiple choice questions. Which of the following is not pointing at a nucleophile? Or which of the following is pointing at an electrophile is another way of saying it. It's this one, that carbon is bonded to an oxygen, so that's electron deficient. Pi bonds, nitrogens have lone pairs, pi bond, those are all nucleophiles, right? They're easily broken, we've been using those a lot. For this one, which reagent will give the product in the reaction above? We went from an alkyne to an alkene. It's a transalkene, so really it should be D. Now I would have drawn in the dot for you because it's sodium metal or lithium. That's the other kind it could be. So that gives you the transalkene. The first one would give you the alkane. This one doesn't do anything for this. That's a strong base. And then Lindlar's gives the cis. Why does reaction below give the anti-Markovnikov product? Remember, anti-Markovnikov means the OH ends up on the less substituted carbon. So why is that happening here? It's not because it's an addition. It is a syn addition, but that's not the reason. It has nothing to do with hyperconjugation or pi bond resonance. It's actually steric hindrance. So this boron is pretty big. It wants to get away from these other bonds, so the boron ends up on the less substituted carbon, and eventually the boron gets replaced with the OH. So it's steric hindrance, right? The bonds, the bigger things trying to get away from each other. Correct name, classic deal. Don't look at the answers. Try to get the answer yourself. So it's 1,3-butadiene. It's not 2,3. It's not 2,3-butene. It's a diene. Z you don't need. because there's H's here, and so these alkenes aren't E or Z. But classic, don't look at the answers, just try to get your own first. So I'm filling the boxes. So you're showing O3 and a cyclopentene. So again, what you really need to be able to do is just cut this down the middle. All right, I just drew it kind of ugly. You don't need to draw it pretty. Right, there's going to be carbon 1 and carbon 2 here are going to have 2 aldehydes, 2 C double bond O's. If you want to draw it like this, that's totally fine. You don't need to draw it pretty and as a straight chain. Biggest thing is to number your carbons. There's no right way to number it as long as you have a consistent way to number it. So it's not naming, so it's not a right or wrong way. Alkene to a syn dihydroxylation, right? You're adding 2 OHs syn. That's OSO4. Here, you're adding H2 palladium on carbon, and you're getting the 2 hydrogens adding syn, because they always add syn. But don't forget, there's 2 methyls here. And I think people forgot that there's methyls here sometimes. So you need the 2 methyls here. That's why it can't be an alkyne, because an alkyne, you'd have 4 hydrogens. There's only 2 hydrogens here. So you have to have these 2 methyls here. Don't forget that these methyls are here. And then this one we didn't cover this year. It's epoxidation. It's a cool one. 4 arrows, but no worries about that one. We'll talk about it later. All right, number 10. So this one I was trying to get you to show you a different molecule, but using something you already know. So I said NIS reacts the same as Br2. So this is something you haven't seen, but if I tell you it reacts this way, hopefully you see it. So again, if you see Br2, you should think 3 arrows, first step, 1 step, making that 3-member ring intermediate. And this time we make with iodide instead. So there's an iodide with a plus charge, but all those same rules apply, the wedges and the dashes. I showed you this adding it in an anti-Markovnikov fashion. I don't know why I did that, just did. But so you just gotta follow where the product goes. This oxygen goes to the less substituted carbon. Normally it wouldn't, but I gave you the product, so you're supposed to draw that. SN2 like there, deprotonation, and then the enantiomer is just this flipped around. So this was a kind of a challenging one in the fact that you've never seen this, but I told you what it's like. And then I made it so you had to do something that your brain doesn't want, you've kind of been training not to do, but I wanted you to see if you could just follow along to see where I wanted you to make. So, all right, mechanism for this one. HBr, 1 equivalent in water. Pi bonds and nucleophile reacts, breaks that. Makes the carbocation. Not worry about rearrangements. The solvent, protic solvent reacts. We get a tautomerization, right? Get that enol. And then finally, H plus just falls off, and that gets us to our product. All right. How about this one, mercury? Make that 3-member ring intermediate. Sometimes you'll see it with 2 arrows. Sometimes you see it with 3. That's fine. 3-member ring intermediate. Same deal. The wedges and dashes. This group and this methyl on the same side. That methyl and this H on the same side. Protic solvent. Water comes in. Breaks the mercury oxygen or mercury carbon bond. This is an alkene, not an alkyne. So we deprotonate. Now we got the OH. See how they're trans to each other, right? And then the sodium borohydride, that's the second step. That just turns the mercury into an H, right? For alkenes, it's different than alkynes with mercury. With alkenes, you just automatically turn the mercury into an H. With alkynes, it has to fall off. We saw that before in a previous problem.